Howdy folks, how's everybody doing today? Happy Thursday. Sorry I'm missing you there on campus. It's caught another cold from my kid here, so I'm going to try and get the mute button if I can. But definitely was not passing the health screen today, and would not really enjoy coughing into my mask over and over and over today. So, thanks for coming along. Good to see you, Chloe. So we'll make do with our usual remote option here, and hopefully that keeps us going and keeps me from coughing on everybody. So we've got a couple things today. We're going to get started on trees. Again, I don't think we're going to finish trees, and that's not too big of a deal. Priority queues builds on trees, so we'll have lots of time next week as well to work on trees. So I think we'll get started on it here, and then in lab, come next Tuesday, we'll actually work on building more functionality into the trees and kind of playing with them, experimenting with them a little bit, seeing how we can interact with trees, just for some silly things here. But trees are very interesting. So we're sort of changing now how we've been dealing with data. So our usual data structures here, let me fire up a new Word document, a new one, I think. There we go. So far, all the things that we've done have been dealing with lists, or sequence data, right? You have the first thing, you have the second thing, you have the third thing, you have the fourth thing, the fifth thing, the sixth thing, on and on and on. So, just a single dimension here of data, or possibly a two-dimensional data, but it's still very sequential, right? So this is very sequential data, which is fine, and we can store a lot of things sequentially. But there are other things that don't necessarily fit in a sequential model, right? So one of those ideas, or one of those things that doesn't fit very well in a sequential model, is even our file system, right? We have our C drive here on the computer. Inside of that, you have all sorts of folders. You probably have a folder for users. You have a folder for Windows. You have a folder for program files, and on and on and on. And then that next level has its own set of subfolders. You might have user A, B, and C. You might have inside of the Windows directory, you're going to have system32. You're going to have all sorts of other nonsense in the Windows directory. Inside of program files, you're going to have n number of programs installed here. And each one of those then, right? So we're going to have, I don't know, let's put in here Word, we'll put Python, and we'll put PyCharm. Each one of those has its own set of directories and folders and structures. So we don't have this sequential sort of structure here with our data. It's not laid out that way. What we have is a hierarchy. Right? So this is our hierarchical data. Hierarchy of data, right? Where there's some sort of root level here, the top level, and then things go down. Now, we like to call them trees, but usually we visualize them upside down, if that makes any sense. So like, here's the trunk of the tree, or the root of the tree, and then these are all the branches that come out here, right? So it's a little different than imagining an actual tree growing out of the ground and growing up. We just visualize it down and out. So it's the same thing, though. Just kind of flip that in your head here when we're talking about trees. That'll help keep things a little bit straight. Okay, so other things about trees, right, which is really cool. There's all sorts of technical terminology when it comes to trees. So a tree has this sort of structure where you have a element here in the tree. So this is a tree rooted at C. So say C is the root of this tree. Now, what's kind of fun about this, the way of defining trees, is that it's a recursive definition. So right here, the users directory is a tree rooted at users. So the tree itself has n number of children that are also trees. So the very definition of the data structure itself is recursive. So it's a tree made up of trees, 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 on as far as we want to go, right? We can have this sort of parent and child relationship. So we'll say, hey, the parent of users is C, and one of the children of C is users. Another children of C is Windows. Another children of C is program files. So we'll say every tree has a parent. Now, the absolute root here, the very top here, has no parent. So it's possible your parent is none in your particular tree, and that's okay. So once you reach a tree node, right, each of these are essentially nodes here. So we're going to say this is a node structure. So we've done linked nodes before, right? We did these linked lists with nodes that point to, hey, here's my previous and here's my next. This time now, our nodes are going to have a different set of structure here. So we're going to have our parent up here, and then we're going to have our data, right, the actual value that we store over here, and then we're going to have n number of children, right? So we don't know how many children we could have, but this is essentially a list here of children, right? Because you can put n numbers of things inside of a list. That works out relatively well. So for any given node then, we can find its parent, right, with a little reference here. We can find the data that it stores, and we can get the list of children out. So generally your children will be sequential, and that's okay. That will mostly fit most of the time. It doesn't necessarily mean we have to have an order to those children, but sometimes it helps. So like I number my children 1, 2, 3, 4, 5, 6. Right? So I know my children are in order, right? So we could sort of draw a family tree using a tree structure, right? That sort of thing. Now, family tree is probably a bad example here because usually you have more than one parent, and that sort of confuses everything here. So we'll pretend that doesn't happen. So those are individual nodes of a tree. So a tree has the root node here. So if we write a tree class, right, it has a root node, right? And a node has its parent, it has the data, and has its n number of children here. Some other terminology when it comes to nodes. So because each of these children is another tree, right, inside of it, you can have what we'll call siblings, right? If both of these trees share a parent here, then great, they're siblings. They're sibling nodes or sibling trees. You might say a node is external or a leaf here. So like this user B, actually that's probably a bad example here because I know it has a bunch of stuff in it, but like B and then documents, right? So if documents is empty, it would be considered a leaf or external. Not a big fan of the external term, but you'll see that. So usually we'll say it's a leaf. So if you have no children, you're considered a leaf in the tree. If you have children, you're just part of the tree, like essentially a branch, right? This sort of idea here. So you can say you can be an ancestor or a descendant here in a tree. So the C drive, my C colon up here, wherever that went, C colon is an ancestor of documents, right? Or we could say documents is a descendant of the C drive with some of these terms here. A lot of times we'll refer to them as subtrees, right? So users is a subtree of the tree rooted at C. Again, there's all sorts of technical terms. It's a little crazy here when we get to trees, but don't worry too much about it here, okay? So we'll say, also when we're talking about trees, you can have edges and paths. So an edge is when you're specifically talking about a parent and child relationship. So users and B, user B here, is an edge. It's a pair of nodes such that one is a parent and one's a child, right, of each other. And then you can have a path like documents B, users C, which is just a series of edges. Okay, so we can follow along that sort of thing here. And now there's a couple different kinds of trees, and Python has a bunch of different trees So there's like a basic tree, and then there's a form of a binary tree or a linked tree. There's an array binary tree and a linked binary tree. It's all sorts of different ways that you can go about building these things out. Again, I find his inheritance to be a little confusing sometimes, so we'll try and do it in what I think might be a little easier here. And generally we're going to work with an ordered tree. So a tree is ordered if there's some sort of meaning among the children. We don't necessarily care what this order of children is here.
Recycled charger gets broken.
Okay, not right now, Vivi. I'm in class. Go. Vivi. Vivi.
It goes recycling.
Please close my door. So if the order matters, right, it's an ordered thing. And that's what we're going to do with our list, because they're already ordered inside the list here. Other times where that order might be particularly useful, there's a great example of like a book can be considered a tree. Right, so book then has different possibly sections. You might have the preface. You might have a conclusion or references. At the end, you might have part A. You might have part B, so on and so on and so on. And then each of those then has different elements inside of it. So part A might have chapters. This might have chapters, so on. References might just have a bunch of references. Right, not necessarily another tree there. And then each chapter could then be further broken up into sections inside of the chapter. Right, here's chapter 6.1, chapter 6.2, like our book literally is. Right, and if you use a table of contents, right, our table of contents, that's essentially a tree structure. Right, here's the section, here's the children inside of it. Here's the children inside of that one. Here's the children inside of that one. As far down as we want to define, we can do that. And at this point, the order does matter. Right, you don't want to be getting those all mixed up. So order does matter here. All right, so why don't we try and fire up PyCharm here, and we'll see how far we can get actually defining just some sort of generic tree structure here. There's a lot of interesting things we'll get into as we start looking at trees. So again, we're going to kind of introduce the topic. We're not going to take a super deep dive into trees. It is typically something you'll cover in a data structures algorithm analysis course. We want to understand some of the basic uses of them, and then they'll set this up for the priority queue structure, the binary search tree structure that we'll talk about in as we continue on working our way through. So priority queues need trees. Search trees is a particular type of tree. So we just kind of work our way through, and at least for undergrads, I'm not as familiar with the graduate track. I'm sorry. The Data Structures Algorithms Analysis course 350 should use this same book, and then it kind of continues beyond past it with some additional material from whoever's teaching it, I believe. So it's been a little while since I looked at all those relationships, but that should be pretty much what it is here. All right, come on, PyCharm, close. I broke PyCharm. Not actually doing anything. There it goes. All right, so let's start up a new project. File, new project. There we go. All right, so this is trees here. All right, so we're also going to look at a little bit of it's not exactly how it all works in other object-oriented languages, but we're going to, we'll at least try and follow along his example so we can talk about some of these ideas of an abstract base class. So we've looked at inheritance, and we said, okay, I can take a class and I can customize it. One of the things that we can do in object-oriented programming is we can define something as an abstract class that doesn't actually work, but it contains all of these shared pieces that from there we will go extend in other subclasses. So if you write a class for tree here, and it can do a couple things, but not everything, right? We're going to say this is an abstract class. And the way that we do that is we write the method, but we don't actually implement it here. So inside of tree then, we're going to have this position idea. So we're going to deal with this position wrapper here. And then positions will have the particular data. They use element. I prefer data. I don't know. I guess we can stick with element. Why not? Element here. And we don't actually know how to do this yet, given this particular tree. So we're going to say we're going to raise a not implemented error. That's all we do. So we're essentially saying it will have this method when you extend this class, but we don't know how to do it yet because there are different ways of creating trees as we look at this like tree hierarchy here. So we can define an equals method. How is one equal to another? And again, we're going to just do this not implemented. So a lot of these are going to have not implemented. What's fun though, you can this not equals method can say return not self equal other. And self equal other will run the equals method. So once we've done an equals method, right, we can do the not equals by whatever the equals one does. But neither of them will work yet. Okay, so that's the nested position class. So all we're doing with position so far is giving you the particular element. Right? We'll have other information in position depending on how we do this as well. And then we're going to say, okay, let's have a root method here. And again, we're just going to do this not implement. We don't know how to give you the root particularly yet. This is kind of boring here, but we're building out an abstract class. We're saying, hey, here's all the methods we're going to have. Here's all the functions we're going to have. When you create an instant, when you extend this class and build one, then you can actually go do it yourself. So given a, no, my goodness, define parent of self given a position. So for now, we're just going to raise not implemented error, but if you give me a position, I'll be able to give you the parent of that position. Right? We're going to say, let's say the number of children given a position. So this idea with that position wrapper, right, what we're working on our lab on Tuesday, is this is how someone will interact with our tree. They'll be given positions, and they can give those positions back to the tree class, ask it to do things with it. So and again, we're just going to not implement right now. We can define a children of a given position. Again, this one we don't do yet, but it's going to iterate over all of the children. And then we can define a length method. Again, we don't know how to do that yet. Okay. Let's see. Then some things that we actually do know how to do, which seems super weird here because they're going to rely on the functionality that we don't have yet. But we can say, okay, we can tell you if a position is the root. Right? So if you give me a position, I'll tell you if it's the root because I'm going to return self.root equals the position. Now, none of this works yet, right? Self-root doesn't work yet. And if I give you a position and check if it equals another position, I can't do that yet. But once I've done this position part and I've done the root part, this is root will just automatically work. Which is super cool. And then we can have a is leaf. So if a position is a leaf position, we can return self.number of children of the position equals 0. Hey, Hollow, how you doing today? Thanks for following along. And then we can define if we're empty, it's empty. If our tree is empty, we're just going to return the length of self equals 0. Remember, we have a length function here. We don't know how it works yet, but once we know how that one works, then is empty will just work automatically for us, which is kind of fun. So these will work for us no matter what kind of tree subclass we write, as long as we write the methods that we said we're going to write here. So it's a little funny here, but this will work here. So other aspects of trees here. We have a couple different things to talk about when we talk about trees. Here, let me just do a new page maybe. So for a given tree here, right, let's do that. Excuse me. Let's do the C drive example again. So C drive, we have users, we have, hey, thanks so much for following along. Program files, we have Windows, right? Users then has A, B, and C. Program files has, PyCharm, it has Python, it has, I don't know, Word, yada, yada, yada. Windows has a bunch of things. System, dot, 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 dot. We don't need too much here. So for any given position in the tree, there's a term called depth. So the depth here is how far from root, right? And that's in generations or levels here, right? So this, we might say, is level 0, this is level 1, this is level 2, right? So the depth of something here is how many generations it is from the root. Well, there's 1 generation to the root. So the depth of the subtree here, or the position here, is 1, right? So everything at level 1 will have the depth of 1, essentially. So we can actually write this now, looking at depth here, because we can say, hey, we're going to define the depth of a given position. We'll say, okay, if the self.isRoot of the position, we're going to return 0. You're done, right? There is no distance between you and the root of that tree. Otherwise, we're going to return 1 plus self.depth of the self.parent of the position. Right, so we're going to write a recursive function here to say, okay, sure, it's 1 because you're not the root. Now give me your parent. Okay, let's add another one. If you're not the root, we'll keep on going. So we'll keep on finding the parent, finding the parent, finding the parent until we find one that is the root. So because the tree is a recursive structure, we can use recursion in our functions here, that it doesn't matter if we have 50 different generations in our tree. The code's the same. Sure, it'll just work its way all the way up. So in terms of performance of this, right, we don't know the structure of a tree, and technically, I can show you a really ugly tree here. I can have a tree that is A, B, C, D, E, F, on and on and on. They don't have to have more than one child. Right? There's nothing that says it has to have more than one child. So this is a tree. It's a linear, like a sequential linear sort of tree. It's just one line here, but we don't know. So calculating the depth for any given position, then, the worst possible case here is O of n, right? Because we don't know the structure of the tree. So, I mean, the best, so this is worst, the best is O of 1. If you ask for the depth of the root, we're done here. So if I have no idea what the structure of the tree is, right, my average really is going to be, I don't know, somewhere in the middle here of n divided by 2. Once we say like all the different positions, and remember we just get to throw away coefficients. So my average is O of n. Not great. Not so great, right? So that's our average O of n here to figure out the depth of a particular node, right? Because we don't know what it is. You know, it's likely not to be like that, but we have no guarantee. Okay. Now, there's another term that we use when we come to trees here. So depth is from a particular position. We also will say the height of a tree. So the height of a tree here, and it can be a subtree, like the height of this subtree, or just in general, the height of the entire tree here, is the maximum depth. Right? Maximum depth. So, sure, we could do that. We could define height here of a particular tree here. Now, the book actually goes through and marks this as like a private helper method here, because for reasons. This is height. This is max depth here. So the height of a tree then is going to return the max of self.depth. Oops, max here. Self.depth of a position for position in self.positions. right? So I can say, hey, here are all of my positions, right? Do we have the, oh, do we not have that function here yet? I thought we had that position, that function. Thought we had a thing. Did we not have it? I missed it. I missed it, friends. Where'd it go? Yep, I missed that iterator, sorry. So there should be another one in here. Define positions of self. This will just return every position. Oh, we gotta raise that error here. Positions. Did I not do it right? Okay, it's fine. So we can get all of the positions out here. So we can say, okay, for every position in self positions, and if we want, we could even specify here to do a little qualifier. We could be kind of cute here. We could say, hey, if self.isLeaf of the position. And this string or the list interpolation, oh my goodness, list expressions? I'm blanking on the term. I'm sorry. This is like horrible single line looping here, but it does. This is the loop. If this happens, right, and then we're taking the max of all of that, of this thing. So if this is true, do this thing here for every position in this here. Hector, thank you so much, my friend. Appreciate you coming on by and dropping those bits. Donating to the Student Scholarship Fund over at the College of Engineering and Computer Science at the University of Michigan Dearborn. Look at that, I got it out in one breath this time. Apparently next week is Giving Blue Day, so there's like some competitions for fundraising and that sort of thing. So we'll be donating the next amount here out for that, which is really fun. Okay, so this will work here. Works. But there's a problem with it here. Right? What did we say happens with the depth operation? Right? Now, on average, it's O of n. Again, we know if we're doing every single position, we're not going to get O of n, but we're going to get O of n over 2 if we do every single position, right? Because some of them will be n, some of them will be n minus 1, and on and on and on and on and on, right? So in terms of performance of this one here, its performance is O of n squared, right? For every n, we're doing n things again, essentially. Sorry, give me a second. All right, sorry about that. The little guy has the same cold I have, and he is unhappy. So this height, then, is not a good way of going about this. Whew. All those cold meds have really got the stuff moving. So a better way of doing this, right? There is a better way of figuring this out here. We'll call this one, this is the height better version here. It says for a given position here. Now we don't know which position it is, but for a given position we can say, hey, if self.isLeaf of the position, we're gonna return 0. Return 0. Otherwise, we're gonna return 1 plus the max of self.height better of the child for child in self.children of the position. So what we're going to do here, we're going to start at the root here, right? And we're going to start saying, okay, let's start adding up and finding the max of the height for every child that we have here. So this calculation here is going to start at the top. And this seems a little funny here, but it starts at the top. It says, okay, let's do it here. And then we'll go to all of our children and find the max of its height, which each of those says, okay, from this position, let's find the max of this height. From each of those, right, finds it. So it only needs to operate on n items. here. So now our performance becomes O of n. O of n, as each node or each position is only looked at once. Can't spell here, friends. Right? So if we're a leaf, we're done, we stop. Otherwise, we keep on going, finding all of our children, finding the max of them, 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 and we just add up whatever the 1 plus the max is for their height, for their height, and for their height, and for their height. So it works its way down using this recursive nature here. So what we want to do then is we want to say, okay, now we can have a height function here that will say, hey, if you don't tell me the position, we'll assume it's none. Oh my goodness, none here. And then if my position is none, we're going to return, we'll say position is equal to self.root, and then we'll return the self.height better of the position. So you can get the height of any position here. If you just ask for the height of the tree and don't give me a position, I'll assume you wanted the root. Does that make sense so far? So again, we don't have much yet implemented, but these heights and depths will work as soon as we figured out how to make these other things work. Right? And we don't know which one is which yet. We'll get there here. So the first one we're going to look at is a binary tree, which is a simpler tree. So it limits the number of children that we're going to have to just 2. Oh, excuse me. I forgot to mute there. I'm sorry. So we'll look at how we can do our binary trees with 2 different structures, and then we'll look at some general trees, and then we have some traversals of trees. So I think actually for now we're probably at a pretty good place where we can pause, and when we get to lab time we can implement a binary tree. I think that might be fun. You know what, let's do binary tree, but not an implementation of binary tree. How about that? So we'll get to that point, and then for lab we can do the linked binary tree and the array-based binary tree. I think that should be a lot of fun. All right, so from here then, the binary tree is saying at most you can have 2 children. So we're putting limits on the number of children here. So we're going to have a class for binary tree, and it's going to extend tree. So we'll take advantage of all the stuff we did here, right? Because all this stuff will be the same here in our binary tree. So a couple things we're going to do with binary tree. We're going to have a left of a given position here. And again, I don't know how to do this yet, so we're going to raise a not implemented error. We'll get to this. This will be different depending on how we write these here. We'll have a right of a given position here. Again, not implemented. So you can say, hey, what is your left child or what is your right child? Right? We can say, hey, you give me the sibling for a given position here. Remember, for siblings, it was the position that shares your parent. So with a binary tree, we only have a right and a left. So the left sibling will be the right sibling will be the left, no matter what it is here. Now for sibling, actually, we can really write this one here. We can figure out what a sibling is. So we'll say the parent is going to be self.parent, self.parent of the position. So I'll figure out what the parent is. And then if the parent is none, we don't have a sibling. We're going to return none. Right? So if we don't have a parent, we're none. Otherwise, we do have a parent. Then we can say, hey, if the position is equal to the self.left of the parent, then what we want to do is return self.right of the parent. Right? If we are the left, return the right. Otherwise, we're just going to return self.left of the parent. So if we don't have a parent, none, we're done. If we do have a parent, if we are the left, return the right. If we're not the left, we must be the right, so let's return the left. And we can define children of a given position. So we're going to say if self.left of the position is not none, Now, yield is this funny keyword here that we can use for iterating over things. We're going to yield self.left of the position. We'll give you the left child. Then, if self.right of the position is not none, we can yield the self.right of the position. So if we have a left, we'll give you the left. If we have a right, we'll give you the right. If that's it, that's all we're done. So this will let us iterate over the children here in our particular binary tree. Because we only have two children. So we have the left, we have the right, and we can get the sibling of a position, and we can get the children of a position here. Okay, so I think we'll pause, and then we'll work on actually adding the linked binary tree in lab. And we'll actually go and use it for doing some things. So far, none of this code actually works here. So yield is it's not return. So it's going to give the value back, but it's going to sit and wait here for you to ask for the next one. Right. So when you do a loop and you say, for n in range 10, right? The first thing it does is it yields 0. And then it waits for you to ask for the next one, because we're iterating over these things. If we just hit a return, all you get is one value and then it's done. There's nothing we can iterate over here. So it's part of this idea of giving something that will iterate in some sort of loop here. And we can say for child in children, and we'll maybe get 0, maybe we get 1, maybe we get 2 when we loop through them here. Yep. So we'll look at the trees here. Yeah, I think we'll do both array-based trees. Oh, do we not do the array? Maybe we don't do the array-based tree. We'll talk about the array-based tree later. And so we'll do the linked tree come lab, and then we'll go and use it for adding some data to it here. I think that's a good point to leave off here, okay? All right, folks. Let me go commit this to GitHub. So we'll do our lab on Tuesday. We'll essentially follow the book here. We're following really closely along here. And hopefully this inheritance hasn't been too bad, and it should make some sense here, because we have all the shared stuff here in the abstract base class that doesn't know how to do everything, but we'll start to be able to implement some things as we go. And now when we have a linked tree in a minute, we'll have actually a final working class that we can actually use then and start adding and storing data places here. Let me find my repo here. We'll commit that. Excuse me. Ooh, those cold meds are getting everything moving. That's awesome. Trees. Yeah, so for lab, for sure, hop on the Zoom with us synchronously. If you have questions, I can help talk you through what we're doing. But mostly we're following along, implementing the linked list on Tuesday, and then we'll go use it to store a bunch of data, which should be a lot of fun. So we can then go look for things inside of trees, and we'll have some fun with it. Okay. All right, folks. You take care, and I will see you on Tuesday.